we have. Today, my presentation is just an overview of all the regional services that we have. My first presentation will be on the EARS, which is the EUMETSAT Advanced Retransmission Service. And then I'll talk a little bit about the upcoming EPSSG regional services. For the direct broadcast EPSSG local processing software, Nigel Atkinson from NWPSAF will provide more information on that. Also later on, I think this morning, what time was that? Yes, just before lunch, some of my colleagues will give some more technical details about our regional services. So I just want to give you an overview, and then if you have really technical questions, hopefully they will be answered in the presentation that's going to come from my colleagues just before lunch. And then, of course, we're here the whole 3 days. So if you have any questions about anything that we touch on, then please don't hesitate to come and ask me. So we have our regional services, of which EARS is a very big part. I've got some roadmap items. So just looking at our regional services, so as I said, EARS, and we're taking the data from the first generation of Metop satellites. We're also taking data from the NOAA satellites. So at the moment, SMPP and the 2 JPSS satellites. And we're also taking data from the Chinese satellites as well. I'll touch on it in my second presentation, a little bit more information about the EUMETSAT regional services for EPSSG. But just to cover that briefly, we'll get the data for that from the same 5 core stations that we have for the EARS services, with an addition of another direct broadcast reception station in the Azores. And the big difference there is we'll do the processing here centrally and make that data available on our EUMETCAST service and also on WIS2. The data will also be available in our data store. The current timeline for the start of the Metop-SG regional data is Q3 of this year. So as I said, the local mission software is the package that you would need as a direct broadcast user to be able to process the direct broadcast data from EPSSG, and NWPSAF will give a presentation on that, in fact, after this session. So here's just a graphic just to show, and I think that most of you coming to this meeting will know how that all works. So the data coming down from direct broadcast processed, and here for the EARS, we send it back to do some post-processing of the data, and then we send it out in our normal dissemination mechanisms. So our targets are that all the data that we receive will be available within 30 minutes. And improvements we've made in the last 2 years have meant that I think, if I could say, 95% of the products that we have are now available within 20 minutes. So we've made great improvements in that area. This graphic is just showing the 5 core stations that we currently have supporting EARS. So I don't know whether you're familiar with that, but we have one in Kangerlussuaq, one in Svalbard, one in Lannion in France, Athens, and Maspalomas in the Canary Islands. This graphic is just showing the coverage of each of those stations. So we have EARS NG, which just stands for the next generation. I think that's everybody's been using that lately. But that was just a refresh. And as I mentioned, that refresh was what allowed us to then approach this 20-minute target for the delivery of the direct broadcast products. Here's just a list of the current products that we have within the EARS service. I think I have a list of those yes. So here's a better graphic of the products that we have from all the different satellites. So hopefully these presentations will be made available to you, so you can use that as a reference to see exactly which products that we're processing and distributing as part of the EARS service. And for our EARS service, for our 5 core stations, and each core station we have 2 separate chains, so 2 antennas and 2 separate processing systems. We set the priorities for the spacecraft. Now, if we're running with 2 antennas, then we have no problems and we can get 100% of the data. There's no conflicts. But if one of those chains should go down, then it's not possible to receive and process 100% of the data, and therefore then this priority list comes into effect. And as you can see, we've split that up into mid-morning, afternoon, and early morning orbits, and then assigned the priorities appropriately. We have a pre-EPSSG and a post-EPSSG priority table there. So yeah, once we become operational with EPSSG, then the table on the right will come into effect. Just as a matter of interest, I put here the EARS daily volume of data. And when you look at that in terms of the volume of data that EUMETSAT has, it's quite a large slice of data. Also looking at all the image type products taking up a majority of our data volumes. Just another graphic showing our the number of registered users for EARS. Trying to indicate that on the 2 columns on the right that this service is increasing, or the number of users using this service is increasing. There's no decrease in the number of users. So our roadmap, we have FY3F and FY3H, but those spacecraft only support left-hand polarization, and we have a bit of an issue. Most of our stations do not support left-hand polarization, so we have to look at a way to update those feeds so we have dual polarization capability. Also, we're trying to ensure that for each site we also have redundant network capability, and we're trying to utilize GEONT to achieve that. And as I said, the Metop-1A regional services expect to start this year, Q3, and launch planned for later on this year for Metop-SG B satellite. Not to steal anything from NOAA or CMA's presentations, but just we got next year JPSS 4 expected to be launched, and FY3J as a replacement for 3E, maybe at the end of this year, but we don't expect that we would have that in the EARS service until 2028 at the earliest. So that was hopefully my brief. I don't know how much time I've taken. My brief explanation on EARS. As I say, that my colleagues are going to go into a little bit more of the technical details of what we do with that. That was just trying to give you an overview of what our service was. And then the next presentation, I'd just like to talk to you, and I don't know where Sreerekha's at the back there. So for this EPSSG regional services, if you have any further questions, then my colleague Sreerekha will be the best person to ask. In combination, I hope that we can answer all your questions. I've tried to bring in some graphics of a previous presentation. And so this is just trying to give you, again, an overview of what the EPSSG regional services are. And this is the differences from what we've done with the first generation Metops and what we tend to do with the second generation. So just to say, we have global data, and that the global data from EPSSG it would have been half dumps from Svalbard and McMurdo, making the capture of the full orbit, but in two halves. And then for the regional data, the data is acquired by the five, as I said, the five core stations, which currently support EARS, and one extra station in the Azores. And that data is brought back to EUMETSAT, processed, and then disseminated to the users. For the local processing, there's a local processing software, which NWPSAF will tell you more about. But just wanted to say there's these three distinct services for Metop-SG. There's the global, the regional, and then the local processing, which is the direct broadcast by any other user. So yes, the data is processed in here in EUMETSAT HQ. For EARS, we actually process the data in the station itself before sending it back here for dissemination. The 6 stations that we have then will cover what was known as the area of interest that was defined for EUMETSAT. The data from the stations is transmitting straight back to the processing facility here. So it's unlike EARS, the data are not processed in the station. So the operational expectation of that, and I don't know why I've stuck my surname at the end of that line, is expected to be at least operational by Q4 for the NWS and the radio occultation data, and then the other products becoming operational in Q1 27. I think that I've just repeated that slide somehow. So just a graphic showing the 6 stations, and then the processing, and then the dissemination. And then talking about the local processing software. The direct acquisition stations acquire and process the data locally is not sent to EUMETSAT for processing. And then this is the data that's normally provided to the NWP centers via WMO-WIS 2. And the local processing software, sorry, where I say here will be provided, is now being made available by the NWPSAF, and you can download that processing packages from the NWPSAF. And this is just a graphic showing for the local processing, there's all the satellites out there in anybody's station, and then making the data available by DBNet. Again, these were 2 separate presentations that were for different audiences originally, and so here's the priority table again, and I think I've explained that already. And the final slide is just a list of information and websites where you can get the information for Metop-SG. And there is some actual EPSSG local processor test data available as well. And I think this is my final one, just showing the our expected flyout chart for Metop. So B1 should be launched very soon, and then in 32 and 33 we got the A2 and B2, and 39 and 40 then A3 and B3. Thank you very much.
Okay, thank you, Nick. So we have some time for questions. Yeah, go ahead, Jess.
Yes, we already got a question through Slido.
Oh, great.
Wang Ping had asked, what is the plan of UMETSAT to provide raw data to level 0, then to level 1 and level 2 for regional Metop-SG stations worldwide?
That's a very interesting question. I may need to think about that for a while. But I don't think that, so as I said, we have the global, the regional, and then the sort of the local, which is more every other station processing the EPSSG data. So UMETSAT has no plan to redistribute that other data, only the data from our regional service. So that would be only from the 6 stations we have, we would disseminate that. There is currently no plan for us to ingest any data from other stations and disseminate it.
Okay, thank you.
Thanks, Nick, for your 2 presentations. Maybe I missed it in your presentation, but what's the current estimate for when Metop-SG-A1 will become operational? Best guess.
So my best guess is it'll be in 2 phases. The first phase will be RO and MWS, and we're expecting that to be in Q3 this year. And then the remaining 3 regional products in Q1 27.
Okay.
That's the target at the moment.
Okay.
All right, if there's any other questions. Yep. Yep, Liam's got another question.
Okay. I could go all day. But could you speak briefly about the current orbit plane configuration of Metop-B, Metop-C, and Metop-SG-A1? I'm not sure that that's widely known. In terms of if someone's out there trying to receive Metop-SG-A1 or Metop-C at the moment, what can they expect?
As you know, I'm not the best person to answer that question.
Okay.
Obviously, as well, the orbital planes of those satellites within their in the different phases will not be necessarily the final. So we have on our websites the TLEs, or the orbital elements, to allow people to get that information for the ones that are currently flying. And if you think that's of benefit, I can provide get some further information about the intended orbital planes. But they'll match what we have for eventually for the first generation of Metop satellites.
I mean, I think we found maybe we received a notification out Wisconsin, but that Metop-C and Metop-SG-A1 are kind of flying in formation at the moment. So you can receive, if you have one antenna, you can receive one or the other, but not both.
Yeah, that's
okay.
That's for the to support the tests that they do for the tandem flight.
Okay, so I think the way, just another.
Yes, we got one more question. Will direct broadcast be available on all future Metop missions?
Currently, it is planned that it will be available on all future missions. There's been no discussions about not having it on any mission.
Okay, great.
Okay, so I think the way we're going to do questions, as Jess mentioned, you're free to type your questions into Slido at any time while the speaker is talking. Then after the session, if you have a question, maybe if you want to raise your hand, then you'll be able to ask your question directly through your microphone just by pressing the button in the middle. So are there any other questions from the audience for Nick? Oh, and could Sreerekha please raise your hand, his co-presenter over there, if you have any questions, please find Sreerekha. So are there any other questions for Nick?
So in closing, I would just say that myself and several of my colleagues are here attending the meeting. If you do think of any questions or have anything you want to discuss, please come and find us in the coffee break or whatever. And if we don't know the answers, we can find someone within UMETSAT that hopefully can give you the answer.
Excellent. Thank you. So we are a little ahead of schedule. Before we go on to our next presenter, we'd like to go around the room and just, if you could, just so people know who everybody else is, if you could please just give your name and institution. We'll just go around the room. And I'll start. I'm Graham Martin from UW-Madison SSEC Sims.
Hi, good morning. My name is Jessica Brown, and I'm also from the University of Wisconsin-Madison.
I'm Liam Gumley, University of Wisconsin-Madison Space Science and Engineering Center. And this is a good chance to practice speaking into the microphone.
Maybe that was a direct comment to me during my presentation. Nicholas Coyne, UMETSAT, looking after the operations of the regional services.
Good morning, Alejandro Aguilar-Sierra from National University of Mexico, LANOT.
Hello, this is Jorge. I work for EUMETSAT and I'm working on years.
Antoine, Jeanjean. I used to work in the engineering of the years services in EUMETSAT. I recently moved to the project management team. So I still will work on the coordination here of regional services, but engineering part has been transferred over to other team.
Hello, I'm Daniel Waltman with Seaspace Corporation.
Okay. Good morning. So I'm Timo Ryppä from Finnish Meteorological Institute, and I'm responsible of our Sodankylä ground station activities.
Hello, I'm Seppo Hasinen from FMI2, and I'm contact point for the sample service, for example, and I'm also the project manager for UMETSAT ACSA. It's not directly related to this one, but just to mention it. Thanks.
Hello everyone, my name is Taiki from GMA. My work is direct readout to LEO satellites.
Hello, my name is Jeanjean. I'm with the UW-Madison Space Science and Engineering Center. I primarily work with data services and also with low data.
Good morning. My name is Douglas Schumacher. I work for the University of Wisconsin-Madison Space Science and Engineering Center, primarily on supporting software for satellite data for the National Weather Service.
Hello, I'm Mitch Goldberg from the City College of New York, and we do have a DB station.
I'm Jen Delamere from the University of Alaska Fairbanks, and we also run a DB station.
Skylar Fennell from Institute for Telecommunication Sciences in Boulder, Colorado.
I'm Rob Stafford. I'm also from National Telecommunications Information Administration in Boulder, and we mostly jam the nice satellite information that you guys are providing all the time and try to figure out what happens when we jam it. So.
Good morning, everyone. I'm Dima. I'm from Aurotech, a startup from Munich, and we try to detect as many fires as fast as possible. So thanks for having me here.
Good morning, everyone. I'm Coyne I'm from the Cooperative Institute for Research in the Atmosphere at Colorado State University.
Good morning. My name is Zabierz Górecki. I'm working in the Satellite Remote Sensing Department at the Institute of Meteorology and Water Management National Research Institute.
Good morning. I'm Richard Wright from Darkcom Systems Limited in the UK. We manufacture direct broadcast and EUMETcast ground stations.
Hi, I'm Danny Hackle from the University of Wisconsin-Madison Space Science and Engineering Center.
Hi, I'm Levi Fons, also from UW-Madison Space Science and Engineering Center.
Hi, I'm Jeff Curitan from UW-Madison Space Science and Engineering Center. One of the CSPP developers, and I'll be talking about OMS Level 2 later in the week. So look forward to that.
Hi, I'm Matthew Odell. I'm also from the Space Science and Engineering Center at UW-Madison, Wisconsin, and I am one of the CSPP developers.
Hi, I'm Mike Butler. I'm an affiliate of NOAA NETSTIS.
Hello, I'm Yanan Liu from East China Normal University. I will introduce my research during my presentation. Thank you.
Hello, good morning, everyone. And my name is Wang Pingyuan. I'm working for Enterprise Electronics Corporation, Leonardo, with the headquarters in Alabama, United States. But actually, I'm living in Melbourne, Australia. And we have around 50 satellite stations for more than 50 countries in the world. Most of these stations are using the CSPP software. So thanks to the CSPP team and the UNISAT for hosting this meeting. Thank you so much.
Good morning. I'm LANOT. I'm from the IGAD Climate Prediction and Application Center based in Nairobi, Kenya.
Morning, everybody. I'm Tembambule from Sansa, South Africa.
Hey, folks. My name's Harry Dove from Here Goes Radio Telescope in upstate New York, and we do direct readout from GOES-R.
Good morning, everybody. My name is Regan Mpiga. I'm from Ejios in Gabon.
Good morning, I'm Larissa Menge from Gabon Space Agency.
Good morning, everybody. My name is Michael Radenborg. I used to work in this place for many, many years, and now I'm a consultant, and I'm supporting WMO for the DBNet initiative that you'll hear about later.
Hello, everyone. I'm Priyanka Roy. I'm supporting NOAA NETSTIS.
Good morning. I'm Tom Hindenes from Kongsberg, tech lead for the MEOS receivers that are used in ears, among other things.
Hello, good morning, everyone. I'm Sreerekha Thonipparambil from UNAM. I am the EPSSG User Preparation Project Manager, and which is why if you have any questions on Metop-SG in general, you can contact me. You don't have to remember my name. Just use ops@umetsat.int. So for any Metop-SG or in general, any questions related to Metop-SG or any other instruments, you please contact at ops@umetsat.int. Thank you very much.
Hello, everyone. My name is Li Hangzhou. I work for NOAA NETSTIS Low Earth Orbit Program Office. I'm the LEO Satellite Product Manager. Thank you.
Good morning. My name is Satya Kaluri. I'm the Chief Scientist for NOAA's LEO program. That includes JPSS, as well as partnerships that includes Metop, Sterna, AMSR, and so on. Be here. Glad to be here. Thank you.
Hello, good morning. My name is Fernando Ibañez from EUMETSAT.
My name is Bruce Flynn from the UW-Madison Space Science Engineering Center, primarily a software developer in the direct broadcast space.
For the people who are in the back of the room, if you don't mind, could you just please stand up and maybe speak loudly and briefly introduce yourself? Okay, and Jess has just reminded me that we have people online. So if we could please, for the people online, please introduce yourself. I guess starting, I'm going to read off the names, starting with Nigel, who's our next speaker. Nigel, can you just briefly introduce yourself?
Yes, hello. Can you hear me okay?
Yes, coming through loud and clear.
Okay, so I'm Nigel Atkinson. I work at the Met Office in Exeter in the UK, and I'm here today with my NWP SAF hat on. The Met Office is the lead institute for the NWP SAF.
Okay, and next, Abani Ahmed Ali. Can you please at least test, if you're able to unmute your microphone, could you please introduce yourself? I see your microphone is unmuted, but we're not able to hear anything. So we'll move on. Next, Dionke Issa Traore.
Hello, can you hear me?
Yes, I hear you. Okay.
Hello, yes. Good morning. I'm Abani Ahmed Ali, working at the African Center of the Telecommunication Department. I'm managing the RARSA Africa network.
Okay, thank you, Abani. And so now, I'm sorry, you're cutting in a little bit and out a little bit, but I think we caught most of your introduction. Thank you. Dionke Issa Traore, please go ahead.
Good morning. My name is Dionke Issa Traore. I'm Administration System in Agreement. Thank you.
Okay, thank you. And I think that's everyone that we had online. So now everybody should know, at least have names to go with faces, and feel free to seek out and speak to the other conference attendees. So let's get back into the program. Nigel, we've already done a sound check. Our next presenter is Nigel Atkinson from the Met Office, and the title of his talk is NWP SAF Support for Local Processing of Metop-SG A1. Nigel, if you're able to share your screen, please go ahead and do that.
Yes, it's just coming. Let me.
Yep, we can see it.
Let me bring up the PowerPoint. Right, can you see that?
Yep, it looks really good. Go ahead, please.
Good. Okay. So yes, so we heard from Nick about the local processor. So I'm going to go into a bit more detail on that. And apologies to those who were at the DBNet meeting last week. There's a lot of duplicate material, but a few new things as well. So, as I'm sure you know, Metop-SG A1 was launched last year in August. It's also known as Metop-D, or at least it will be when it becomes operational. It's still in commissioning. The data are starting to flow, and if you're keen to test the direct broadcast, the first batch of packages is ready for you. So, what have we got that is supported by the NWP SAF? Well, first of all, what does the NWP SAF do? If you're not familiar, it seeks to make the EUMETSAT products useful for NWP purposes. So that's its prime function, and we're supporting two aspects of Metop-SG. First of all, the direct broadcast software. This is to go from raw data to processed level 1. And the current status is that the MWS, the microwave sounder, and the VII MET image processors have been released. So VII is another name for MET-image. It stands for visible and infrared. I can't remember what it does stand for. Anyway, it's another name for MET-image. And the YASI Next Generation, or the IAS, will follow quite soon, we hope. So that's the direct broadcast processors. Then we have what we call AAPP-SG, a second generation of AAPP-SG, of AAPP, which I'm sure some of you are familiar with, and that ingests the microwave sounder and YASI Next Generation files, and it converts to buffer, as is often required for DBNet and other NWP applications. And the status of that package is that it's under review. The review process is underway. We expect to release it very soon, hopefully later this month. It's a new package. So I will talk about those in turn. First of all, the direct broadcast software. So where's this come from? It's the overall responsibility is with EUMETSAT. We in the SAF, we've not actually written any of the code. So if you find something doesn't work, we're happy to take questions, but we might have to refer to them to EUMETSAT. And it's what's called re-engineering of software for local mission use. And that's been done by industry under contract to EUMETSAT. And you can see the contractors listed in that table. And the NWP SAF has taken responsibility for the distribution and user support of those packages. So here's an overview. Let me see if I can get my pointer working. Just a moment. It's in there somewhere, but I can't find it. Never mind. I'll describe it. So you've got the reception station. You've got some hardware at the front end, a demodulator, and that will hopefully give the VCDU files, which I'll talk about in a minute. Those feed into the local processor. First of all, a level 0 processor, followed by a level 1 processor, which is instrument specific, and that will give level 1 products which can be processed onwards. I've said to AAPP-SG. So this figure is taken from the EUMETSAT direct readout guide, which is a very useful document. What does the VCDU look like? Well, if you're interested in the technicalities, there's the table taken from the EUMETSAT document. You can't make much sense of the raw data as it comes down, but because it's all encoded and pseudo-randomized, but you can fairly easily decode it with RT-STPS, and that may well be done on your front-end systems, but it can be done offline if necessary. You need to get to transfer frames, or VCDU, and they can be found straight after the sync marker. And it's recommended to configure RT-STPS such that the instrument streams are separated. Otherwise, if you don't, then it'll take a huge amount of time to process the very large files that you end up with. That's the VCDU. Then, of course, you have to run RT-STPS, and we had a bit of an issue with that on our system. First of all, the vendor tried to run RT-STPS on the receiver system, and that actually caused a lot of problems, as you can see from that image on the left, which I've called bad. We then disabled that only a couple of days ago, and that actually solved the problems that we've been having with dropouts. So we are now running RTSTPS after the raw file has been generated, but that's quite time consuming. So there may well be a better solution to this issue, but for now, that's what we're doing. Those are MWS images. So what do you need at the moment? You don't need the whole lot. You need the NAVAT packages, the YASI Next Generation packages, the MWS VCIDs, and the MET-image ones. You can throw away anything that's related to GOMI because there's no local processor. And yeah, we assume that the string is that VCID and then the number is present in the file name. It's recommended that you should do so. Okay, so moving on to the local processors, we've got a user guide, which is linked from the NWP-SAF webpage that we've set up. Now you can find it quite easily from the top menu. So the package files are posted on the NWP-SAF website, just like any other piece of software. You have to have an account on the server, which is free, and then you tick the box for each processor that you require. I'll give an example in a moment. And at the moment, we've got those package files. So we've got a level 0 package, an NWS package, a VII package, and some wrapper scripts that we have put together to make life easier for you. YASI Next Generation will hopefully be added at a future date quite soon, once we've got got authority to release the package. Yeah, just this is the page where you actually select the packages, and the ones I've highlighted in yellow at the bottom are the 4 that we're talking about in this presentation. You will also need some ancillary files and some test data, and those can be freely downloaded. You've got some test VCDU data. There's a file of optional CADU test data, although that's not so useful as the other one. There's a couple of auxiliary files. The first of which is quite large, that's why it's posted separately. And then there's a documentation package. So this is not the NWP-SAF documents, it's the documentation provided by the software, provided by industry and by UMETSAT to describe the details of the packages. But hopefully all the information that you'll need as a first look is in the NWP-SAF documentation. What else will you need? So if you want to run the software in real time, you will also need access to the UMETSAT data store, because that's where some of the ancillary files that regularly need to be downloaded are posted. So you will need the EUMETSAT tool, and that is available on the page that I've listed there. And we assume that EUMETSAT is available in your path. So you'll need to arrange for, well, it's all handled automatically in our scripts, but the predicted orbit file is needed daily, and that's checked. There's a daily check as to whether the file is up to date. So the form of the packages, they've been pre-built by UMETSAT on Red Hat 9. We recommend that you use those pre-built binaries because it's much easier than compiling the software yourself. And they need some dynamic libraries, which are included in the NWP-SAF wrappers file. So those will work on Red Hat 9 or other compatible systems like Rocky Linux 9. If you want to run on a different operating system, for instance, we've got some old Red Hat 7 servers, but we've been able to get those to run the software using Aptainer. And the simplest way, especially if you haven't got root privilege, is to create a sandbox, and then you simply enter the Rocky 9 environment. And that works fine, provided you've got permission to create a sandbox, which I think most Linux systems will have. You can get source code. Well, the source code is actually included for the level 0 processor for MWS and IAS. It's not terribly easy to build, but if you need source code for METImage, that is handled separately, and you need to contact the EUMETSAT help desk because there are some export control restrictions on that. So yeah, in fact, MWS is easy to build, but the other two, you need some pieces of software. It can be done. Okay, so we've provided an installation script. All that does is it unpacks the program files. They're what are they called? Yeah, it unpacks each of the instruments and installs them in the location defined by the vendor. But you can put them underneath a directory of your choice. So you don't need admin privilege to do all this. But if you do have admin privilege, you can centrally install them if you wish. So that's the structure that you'll end up with if you follow the installation script. What do you need in terms of computing resources? Well, it's it very much depends on the instrument. So MWS, you can almost run it on a single core or a very small number of cores. METImage, you need at least 16, otherwise it runs very slowly. And for Yazi Next Generation, we recommend at least 64 cores, 128 gigabytes of memory. You can run it with fewer, but it'll be slow, and that will sort of detract from the benefits of direct broadcast. If you've got more than 64, then by all means use them. You can get it to run faster. And we do recommend when you're starting off with these packages, start with MWS because that's easy and it's quick to run. You can immediately see whether you're doing things right. And I'd also point out that for the Yazi Next Generation processing chain, you need to first of all process VII METImage to level 1B. So EUMETSAT have provided some test data, which is included in that file that I talked about that can be downloaded. We've provided a script that will process that test data. It's very easy to run. You just set a couple of environment variables to point to your installation location and your data location, and then you run the test script. In this case for MWS, it'll run the level 0 processor, the level 1 processor, and it'll generate level 1 files. It'll also copy the ancillary data that you'll need first time it's run. And there will be a new test case quite soon to support Yazi Next Generation, because you can't run the Yazi processor with that old set of test data. Okay, so then let's assume you've got your own data that you want to process. Well, there's a main wrapper script there, and run EPSSG. The best thing is to look at the user manual. It'll tell you exactly what to do. But remember that the SGA-1 satellite is still in commissioning, and there may be configuration file updates at some point. We will try to post relevant information on that web page that you see there. A little bit more detail on YASI Next Generation. So it includes an optional cloud mask that goes. So the cloud mask is one of the data fields in the level 1C product. If you want to generate the cloud mask, you need to download and run the Nowcasting SAF's PPS package. So this does somewhat complicate the processing flow, and I won't go into details in this talk, but you can run it without the cloud mask. It's probably simplest to do so initially. So there's more details in the user manual. What sort of runtimes can you expect? Well, MWS, it's a matter of seconds to process a typical overpass. YASI Next Generation is a lot slower. So first of all, you've got to run the level 0 processor, and we find that the level 0 for VII takes about 5 minutes almost. It's quite time consuming. And then you've got to run the level 1 for VII. That's a few minutes, and then you feed the output of that into level 1 for YASI Next Generation. And that is in with 120 threads and 240 gigabytes of memory. Even that took 900 seconds. So the whole thing was around 20 minutes, and I'm not including any RT-STPS runtimes in that figure. So it's quite substantial. Now, there may be ways to speed that up, especially if you can process RT-STPS and VII while the acquisition is in progress. That will need you to have a fairly hefty front-end server, and we haven't gone down that route ourselves. So we're interested in your feedback on that aspect. Yeah, just to say that those figures are from our virtual servers that are not actually on site. We've procured some new on-premises servers at the Met Office. They're not built yet, but we will test the packages on these servers as soon as possible. Let's see if they're any faster than the Azure system that we're currently using. So that's all I've got on the industry supplied processors. I'll just say a little bit about APP-SG, which is the successor to AAPP. Well, it's not replacing AAPP, but it's providing support for the new instruments. So we expect the first version to be released this year. Well, this month actually. Is currently in the final stages of the review and approval process, and it includes facilities for processing MWS and YASI Next Generation. If you want to generate imagery, then that's not included in AAPP-SG. I'll come to that in a minute. So for MWS, you can do things like spatial filtering for NWP purposes to lower the noise. And you can generate some cloud and surface parameters, or if you want to, you can just run the buffer encoding to match the EUMETSAT global product. For YASI Next Generation, there's options like converting from level 1C raw spectra to level 1D PC scores. If you're getting the global or if you plan to get the global level 1D product from EUMETSAT, this allows you to generate the same thing with direct broadcast. So we will at some point be comparing the two products, the global and the local, and making sure that they agree. We haven't been able to do that yet because there's no level 1D global product yet. And I would point out that YASI Next Generation is still in commissioning at the moment. So EUMETSAT are just starting to release level 1C spectra to CalVal users, but not yet the level 1D. That'll come. So what's the AAPP-SG code look like? It's written in Fortran 90. Just like other packages that you may be using, such as IRSPP and MWIPP. The IRSPP, if you're not familiar with it, is for processing the MTG IRS hyperspectral geostationary sounder, and MWIPP handles microwave images. And you will need things like EC codes, NetCDF, HDF5, all standard libraries. And we provide a build script to help you with that process. Just a quick word on buffer sequences. Buffer is one of the normal inputs to NWP. Some centers rely on buffer, others it's not so necessary. But for MWS, the buffer sequence is finalized. EUMETSAT are distributing the buffer data and it looks fine. We're quite happy with that buffer sequence. YASI Next Generation, the level 1C buffer sequence is fairly stable, but it's not finalized yet. And the level 1D is also not yet finalized. So there may well be changes to AAPP-SG in that area. So look out for future updates. I'll just briefly mention the other packages relevant to Metop-SG. So you'll probably be familiar with SatPy, part of PyTroll, and that I believe that's now capable of creating metimage imagery. And then there's the Nowcasting SAF's PPS package, which I mentioned earlier in connection with the metimage cloud mask used in the YASI Next Generation processing. And NWC SAF are also preparing a package which they call PPS Microwave, and that'll handle MWS and also the microwave images on the B satellite when that's launched. And no doubt there are other packages relevant to Metop-SG, and I'm sure you'll talk about those in the next couple of days. So that's all I've got to say. So turning to the conclusions, direct broadcast processes for MWS and metimage are available. YASI Next Generation is coming soon. Give it a try. And we welcome feedback on your experiences. You can either email me directly or use the NWP SAF help desk. And the help desk is not just for questions, it's also for you to provide your feedback and suggestions. So thank you.
Thank you, Nigel. We have some time for some questions. Before we get to that, I'd like to ask the poster presenters to please come up here and line up on this side of the room, and you'll be giving your 1-minute poster introductions. If you could please try to get in the order of your posters, that would help things move along. And if you're wondering, if you don't remember what the number of your poster was, it's on the back of the program. Okay, so if people can please line up here. And in the meantime, we'll take questions for Nigel. And I think we'll start with people in the room. If there's anyone in the room with a question, I already see a hand going up over here. Please raise your hand, and we'll start with Liam.
Thanks for that very information pack briefing, Nigel. So early on in the slides for the local processes, you said that you mentioned this term re-engineering. So
Yep.
I'm trying to understand what that means exactly. Does that mean that the software that was developed for med-image processing that runs in global operations at EUMETSAT has been re-engineered to support local processing?
Right, it actually differs according to the instrument. In the case of YASI, yes, that is exactly the case. So it is the same global software that has been re-engineered for local purposes. For the others, I think I'm not entirely sure, but I think the MWS started out as a EUMETSAT prototype, and it's not the same software as the global. Although it has commonalities, like it uses the same ancillary files, so you should get the same answer. VII, I'm not so closely involved with the history of that. It may have started out as a prototype. So yeah, the global and the local processors, they will have common roots back in the past, but they're not directly descended from each other. I hope does that answer the question?
Yes, it does.
Yeah.
And just to follow up on that topic, and maybe the user guide for the local processor includes some information on this topic, but what can you say at this point about the correspondence or the matchup or agreement between the local processor level 1 data versus the global level 1 data once the satellite is declared, the satellite and the sensors are declared operational? What kind of level of agreement can we expect between the level 1 products?
Yeah, they should be, the level of agreement should be conforming to what the DBNet recommendations are, which is something like the brightness temperatures should agree to within something like 20% of the noise level, or 20% of the accuracy requirement. So the differences should be small compared with the overall uncertainties in the product.
Liam, can I answer?
Yes,
Nigel?
Sreerekha.
Yeah, the end user requirements document of Metop-SG, the requirement is that the local and global products should be within 10%.
10%, thank you. Yeah.
Yes. Yeah.
So, sorry, was that within 10%?
Yes.
10% absolute or 10% of the noise?
No, 10% absolute. The agreement between local and global products
should be within 10% absolute.
Yes. Yeah.
Okay.
Yeah. We will be testing that as soon as we get stable products, and so yeah, that's all going to be investigated soon.
All right. Once again, poster presenters, can you please line up on this side of the room? Maybe I wasn't clear, but if you could just please stand up and come over here and line up. Thank you. Thanks for getting us started, Jeff.
Are there any other questions?
Yeah, are there any questions from within the room? I think we've got some on Slido. Yep, go ahead.
Thank you for your talk. What does it mean stable spectra for IASI level 1 or level 1C? What does it mean stable?
Oh, I just mean that that EUMETSAT have finished changing the ancillary files, like the spectral calibration, the files that influence spectral calibration and that sort of thing. And so we wouldn't expect any changes in the product, because at the moment it's still in commissioning and they could change the ancillary files. That's what I mean by stable.
Okay. Quick one, Liam.
Yeah, I do have one more. And perhaps Nigel can answer this, or perhaps one of our colleagues from UMETSAT. Let's say that someone in the room has already downloaded the software, the level 1 processor, the local processor, and they're receiving Metop-SG data and creating level 1 product from MWS and MetImage. What can they do with that product? What is the UMETSAT policy on dissemination of that data at this time?
Do you want to answer that, Sreerekha?
So
I know what my answer would be.
Nick is preparing to answer, I suppose.
Oh, Nick, thank you. Yeah.
So the distribution of that data would be in line with have to be in line with our data policy, and our data policy for that data is then the same as the Metop first generation. So that means for those direct broadcast data that users receive and process can be freely distributed.
So just so I'm clear, you're saying that whatever I can do today with Metop-B or Metop-C data, I can also do with Metop-SG A1 data.
That's correct.
Thank you.
Okay, Jess, maybe one question from Slido before we do the poster introductions.
Sure. We do have several questions. Just quick before I give you one, Nigel, could I follow up with you and send you the additional questions that were received from your talk?
Yeah.
And ask. Okay. So
I can reply to them by email. Shall I?
Okay, you can. Yes. I will send you an email. So
Yeah.
if we didn't get to your question, I apologize just due to time. So the last question is just the first one that came in. Does NWP-SAF have a recommendation for the granule length to use for MWS and MetImage direct broadcasting level 0, level 1 processing? The default appears to be 3,600 seconds.
Yes. So that is that's what we put in our wrapper scripts. You can have whatever you like, but we find it easier if the direct broadcast is all in one file. For instance, one file per instrument. It makes it easier to cope with. But it is quite common for MetImage to use smaller granules. If you're trying to process MetImage in real time, you would want to work with small granules. For MWS, it doesn't really matter. But Yazi Next Generation, you do need to process the whole pass at once, because it relies on the processor relies on being able to see the whole pass. So it's really up to you as a user. But yeah, we find it convenient to have one file per instrument.
Okay, thank you, Nigel. And to those of you, again, I will follow up with Nigel with the questions that are in Slido, and I will try and make sure that we get answers back to you per your questions.
All right, thank you, Jess. Let's have a round of applause for the presenters in this session. And now we'll move on to the poster introduction. So we're giving people an opportunity to just give a 1-minute introduction to advertise your poster. As a reminder, the posters will be set up right around the corner, and the 2 poster sessions will be in today's breaks. But I believe the posters will be up for the duration of the meeting. So you'll be able to come back to the posters and hopefully catch up with the presenters later if needed. So the first poster is okay, Bruce Flynn and Liam Gumley. Maybe I see Liam's in the front. So the title of the poster is Antenna Control System, a new antenna controller for direct broadcast satellite data reception.
Bruce, did you want to speak about that one, or?
Take it away, Liam.
Okay, thank you. So our first poster is on Antenna Control System, or ACS, and it's a new software system for controlling the scheduling, reception, decoding of data on CPI orbital antenna systems, which several of you in the room operate. At UW-Madison, we have currently 5 CPI orbital systems that are located from the far western Pacific down to Central America and the Caribbean. We've used the orbital EOS-FES software system for many years, but in the last 6 months, we've now developed our own software replacement for EOS-FES, so we can control those antennas without needing the EOS-FES. That has a number of benefits for us, including it's a very compact software package. It's basically one binary and some associated utility programs. It's very easy to configure. It's easy to monitor. And it's what has allowed us to receive Metop-SG A1 data starting back in December of 2025. So there's a number of other benefits. Stop by the poster and you can meet Bruce, who's the developer of ACS. You can meet Douglas, who has a lot of experience with deployment and testing of ACS, and I'll be there as well. A second poster is on, excuse me, CSPP-LEO software and products, and it's really an overview of all the capabilities of CSPP-LEO as they exist today. We review and describe the different software packages that are available today, and we talk about some of the features of the recent releases that we've provided to the DB community in the last 18 months or so, including completing our support for NOAA 21, and also talking about some upcoming releases that will complete support of the sensors on board NOAA 21 and NOAA 20 and SNPP, in particular support for OMPS, Nadir Profiler and OMPS Nadir Mapper. That's it from me.
Okay, next is Matthew Odell from SSCC Sims, who will be presenting Digital Archaeology and Automated Architecture, Modernizing Legacy Satellite Pipelines with AI Chatbots.
Alternate title is Cognitive Amplification in Satellite Science Ops. And our primary focus with this solution is that we have legacy pipelines that build most of our CSPP packages that often run into issues with repeatability and discoverability. So I've used AI-developed tools to make the build process more modernized and to make that more repeatable and accessible, and hopefully, to some extent, make it accessible outside of the CSPP team.
Next is Durgesh Nandan Piyush from NCMRWF, who will be presenting validation of EASI Level 2 temperature and humidity profiles using radiosonde observations over India.
Yeah, so in our work, we have tried to validate IRC Level 2 temperature and humidity profiles using radiosonde observations available over India. So most of the radiosonde observation available over India is over around 00 UTC, and if you see the pass of IRC over India is around 5 to 6 UTC. So we also have 2 experimental sites from IITM, one at Solapur and one at Bhopal. So we use those profiles to validate it. It's not a complete work. We have initial assessment. So I'll ask you to just stop by our poster.
Next is Gwyn Utmark from CSIRA CSU, who will be presenting GeoIPS, extending an open source geolocation data framework into level 0 processing.
GeoIPS is software that was developed 17 years ago by the US Navy to make the maintainability of code easier, and it's since been open source in the last 4 years. We're about to release a version 2.0, which updates it to a lot of more modern coding practices. And it mostly takes level 1 data all the way up to level 3, but we're working to extend it into level 0 with some CSPP wrappers. So please stop by, ask some questions, offer some suggestions.
Next is Jeff Yerger from SSCC SIMS, who will be presenting a novel mechanism for managed egress and privileged access in meteorological data distribution.
Yeah, hello. With my work at SCCC, primarily on the data center services team, we often are running, excuse me, a solution that we're often coming to solve is how to manage the access control for our data sets as they're provided primarily to our scientific, commercial, and industry users. And over the past few months, I've been working with some members of my team to create a unified interface to provide access to a myriad of different data sets all through a single interface that is self-managed through users, that allows users to go through the registration, access provisioning, and even like a data access automation process all through a self-managed flow in a single website. And I'll be presenting the architecture that is powering that.
And finally, we have a poster from Jeremy Jacobson and Starry Manoharan, but I see Lihong Zhou from NOAA. The title is Ancillary Data Services for IPOP and Simulcast.
Thank you. I'm presenting for my NASA colleagues who could not make it. So the poster is from Jeremy, Starry, and Ariana, and they're presenting the presentation is about the sunsetting of the Direct Readout lab. So after 20 years of a service, the lab is stopped the service planning November 2026. So for any of the users still using the software and the data, recommend transition to the University of Wisconsin CSPP for any of the tools, software, and data. The poster has a very specific, detailed information about the timeline of the transition. So please stop by and take a look if you're still using DRL. Thank you.
All right, thank you. Let's have a round for our poster presenters. So now we'll have a 30-minute break and poster session. Please help yourself to refreshments and be sure and stop by the posters. And please be back in the room. We'll start again at 11 o'clock. So if you can try to be back in your seats by then, that would be great. Thank you.
And for the poster presenters, obviously feel free to take a short break, but we do ask and to stand by the poster so if people have questions so they can engage in discussion with you. Thank you. Hey, good morning. I hope everyone enjoyed the posters and the break. We're going to go ahead and get started with our second morning session. So our first presenter of this second session in this morning is Alejandro Aguilar-Sierra. And so there is, remember to speak close to the microphone.
Yeah.
And you can go ahead.
Thank you. Good morning. I am Alejandro Aguilar-Sierra from the National Laboratory for Earth Observation, or LANOT, at the National Autonomous University of Mexico, UNAM. Today, I'll be sharing with you how we operate CSPP, GEO, and LEO in our environment, alongside our in-house high-performance software developments. LANOT's primary mission is to receive, process, and distribute satellite data in real time. Our goal is to support early warning systems for severe storms, wildfires, and volcanic emissions and flood. We serve key national entities, including the Mexican Navy, the National Center for Disaster Prevention, and the National Meteorological Service. Here you can see some of the entities that are in any way associated with LANOT, including you, CSPP, yeah. Our physical infrastructure starts on our roof. We operate multiple antennas for polar orbiting satellites, GeoNetcast, and direct reception from GOES-19. This capability is the absolute foundation for our real-time processing. Did you go to the roof when you visit? No, you? Moving to the computing side, our cluster is divided into two main partitions. The data world partition handles data ingestion and heavy processing, running mainly Rocky Linux 9. This includes our main two servers, Cirrus and Stratus, as well as our GPU nodes equipped with NVIDIA Tesla T4 cards. This is like a band of Edison, factory. The products are becoming raw, level 0, level 1, etc. The data service partition manages storage and distribution, utilizing high availability failover to ensure our products are continuously accessible. These are some in-house developed algorithms. One is for hotspots from ABI imagery, from fires. Another is sargassum monitoring, and we are using a lot of other satellites. In this case, Sentinel-2. And for the volcanic ash detection, we use both ABI and theirs from the NOAA constellation, NOAA JPSS. Also, we have developed some software solutions that I will talk about. This is the historical data retrieval system in which a user can ask for some data. Historic means from 1918. That is when we started to archive this data. And there is a interface for the user, a web interface using Django, but it uses APIs to get the data. The historic server gets retrieves local data from our own server and has automated AWS S3 fallback in case we don't have that data, we get it elsewhere. And Tempo FTP allows to create temporal, ephemeral FTP accounts in order to allow the user to download this data. I think this is similar to other services, but what makes this, you will see, very useful is the easy way that you can get a lot of data. This replaces manual requests, transforming it into a fast self-service pipeline for researchers. This is one example of the use of this system, because for this project, we needed a lot of data from 2019. And by the way, we extend our sincere gratitude to the CSPP team at the Space Science and Engineering Center, at the University of Wisconsin, for their invaluable support providing critical ancillary data. So we could run a modern version of CSPP-Geo AIT framework to process historical data, especially to Katy Stravala, that is not here, but I hope she's doing well. The contribution directly enabled the generation of level 2 products, including deriving motion winds and our own ash detection algorithm from over 20,000 GOES16 ABI L1B datasets. We already submit a paper to the Journal of Applied Volcanology. This is just an example of our algorithm detecting ash, right? Now the CSPP Geo pipeline. For geostationary data, our pipeline starts at the raw GRB stream. We use CSPP Geo to generate level 2 products for both ABI and GLM. This provides us with an archive of products ranging from cold moisture imagery to derived datasets like hotspots, flood mapping, etc. What you can see in this diagram is how we all the process. We archive L1B data since 1918 and L2. And sometimes, as we did for the ASH project, we want to reprocess, because the AIT program have some improvements that can be useful for us. We start with, we do all this, and then we use our Geo2Grid to create the GeoTIFF files and other things, the RGB composites. But recently, we started to use our own software, HPSB. I will talk about it now. And MatDrawer is just a Python program to decorate the views with our logo, with vector layers, with timestamp. U2Grid, I will talk about it. And the final products that we distribute in our servers for our clients and users. HPSAT views, or HPSV, high performance satellite visualization. Actually, I was developing this 8 years ago before I knew about Geo2Grid. And the problem is that I hadn't solved the Rayleigh atmospheric correction. So we started using Geo2Grid, or a combination of Geo2Grid with our software for years. But we had the need to get these products faster. So it was a good motivation to finish this software. Actually, I studied Geo2Grid to see how it did it using PySat lots. PySat published lots, and I am doing the same. So it's thanks to Geo2Grid that I was able to finish it. Now we use it for TrueColor, DayNet Composite, and other RGB products, cloud optimized objectives. We can use band algebra to produce more RGB composites. And the performance, full disk, is about 20 seconds against 3 minutes compared to GeoGrid and GDAL in the same server. Of course, in a faster server, both will be faster, saving about 2,300 processing hours per year at LANOT. HPSV is purpose-built for fast operational visualization. It complements, not replace. It's not the purpose to replace Geo2Grid because it's very specific for a need. But if there is any interest, I'd like to talk with Geo2Grid developers. No? It is a GitHub at this address. GitHub, yeah. All right. Now, our pipeline for, I think, all right. Our pipeline for CSPP LEO. Switch it to low Earth orbit. We're using now CSPP for everything after the IPOP demise because of the lack of, the finish of that project, no? Yeah, that was supporting IPOP. Now we use CSPP for all the pipeline. This workflow handles everything from raw to all the levels, level 1, 2, 3. Calibration, geolocation, and the generation of environmental data records using sensors like VIRS, ATMS, and CRIS. And this is our current pipeline. Now, as suggested by Liam 4 years ago, I guess, using containers. We are now using containers. These containerized workflows are currently being deployed across our distributing processing software. So we use STPS on the version in CSPP, no? The one with the latest patch. Then the SDR level and the environmental data records, EDRs. And at the left, you can see the container, the uptiner or singularity container, and at the right, the script we use to run it. This is, we can improve this yet, but we started doing this separately for each EDR, and we will reorganize that later. We are in the process of improving this. And we use Polar2Grid to generate all the geotiffs outputs and MapDrawer to add our decorations and vector layers. These are some of the products that we are distributing for the atmosphere. Well, several products. Obviously I didn't include all. This is just an example. To color from the surface, very important NDVI, EBI, and others. And ocean and lakes. Flood, I knew the author of Flood in Chengdu, I think. She was there, no? And this is Chapala Lake, and is the biggest lake in Mexico. And there's been always concerns about if it is reducing its volume or is recovering, no? Red color means good news, is growing. Next steps at LANOT. We are working now in the infrastructure modernization. We are in the way to migrate processing cluster to Slurm worker manager, replacing manual bash scripts with dedicated data work and data service partitions, as I explained at the beginning. Deploy high availability storage with several new or recent protocols. We are still trying them. This is not definitive. Another software to monitor cluster health and service status. We want to do containerization in order to be able to distribute all this processing in our cluster. You know, if a server is busy, we use another one, just because we using the advantage of the containerization. All right. And as we have NVIDIA Tesla T4 GPU nodes, we are starting to experiment with artificial intelligence and deep learning and all that. We have an ongoing master in science thesis in the detection of sargassum. In conclusion, LANOT has successfully integrated both CSPP, LEO, and GEO into a reproducible containerized pipeline. Our development of tools like HPSB proves that targeted C-based optimization can drastically reduce latency in a real-time operational environment. Finally, our transition to a Slurm-managed fault-tolerant cluster position us well for scalable future processing. We remain committed to the CSPP community. Container receipts are openly available, and planned containerization of CSPP, GEO, and Metop pipelines will further align with our infrastructure with reproducible science standards. And now I open for your questions. Thank you very much.
Thank you very much, Alejandro. Are there any questions? And I see Liam. Go ahead.
Thank you, Alejandro. It's very interesting what you've achieved. I have two questions, actually. Regarding your HPSV, what makes it fast?
Good question. Basically, about things that is compiled instead of interpreted like a Python. Geo to read is in Python, right? And the other is the parallelization. It uses OpenMP, so it uses the available cores in the server. And my plan is to improve it to use GPU. So it will do fine parallelization in the future. It will be faster.
Okay. My second question, can you say something about what's the advantage in your environment of using containers compared to a normal installation of CSPP software?
Mainly, we have a heterogeneous cluster with different versions because it was built over time. No? And we try to run some software and it doesn't work in any server. So as someone told, I think the previous presentation, that they run something so successfully in Rocky 7, no? Using a container with Rocky 9. It is something similar for us. Using a container, it let us run in any of our nodes in the server. So basically, and something in the CSPP Leo, we were using Clarks, and Clarks has not been updated since 2019. So it was not running in any of our servers until we did a container using CentOS, the last version of CentOS. So that's a good example of. Anyway, we are not using Clarks anymore because Atmos has its products, no?
Okay.
But it's a good example.
Very interesting. So you mean ClaverX?
Yes.
Okay.
Yes.
All right. Very good. That's very interesting. Thank you.
This is from last year, as you can see.
Sure.
Currently, we are not using Clarks. We are using Atmos.
Okay.
Are there any other questions? Graham, are there any questions on Slido?
No, I'm not seeing any questions on Slido.
Okay. All right.
That's it.
Thank you, Alejandro.
Thank you.
Oh, I'm sorry. Hang on. There is one question that just popped up from Gwyn Utmark. For your containerized architecture, are you using any orchestration frameworks, K8s, etc.?
Like what? Like Kubernetes or
Kubernetes?
No, we are not yet. We are starting to try this technology, maybe in the future, but currently no.
Okay, thank you.
All right, thank you, Alejandro.
Thank you.
Okay, our next presenter is Nasu Taiki, and he will be giving a direct readout activity of LEO satellites, as well as an overview of Himawari 10. And you can go ahead and get started.
Good morning, everyone. my name is Nasu Taiki, and I'm responsible for direct readout operations of LEO satellites at the Meteorological Satellite Center of the Japan Meteorological Agency. Today, I talk about MSC's utilization of LEO data and an overview of the future satellite system Himawari 10. My presentation is divided into two parts. In the first part, I will introduce direct readout activities using CSPP at the Meteorological Satellite Center of JMA, as well as the utilization of LEO data. In the second part, I will present an overview of the Himawari 10. First of all, I would like to briefly introduce the Meteorological Satellite Center, MSC. MSC was established as an auxiliary organ of JMA on the 1st of April in 1977. The mission of MSC is observe meteorological and related phenomena from space using satellites, process observation data, and disseminate information and product derived from the data. These are main activities of MSC. Next, I would like to give an overview of JMA's direct readout activities. JMA has acquired direct readout data from LEO satellites since 1968 and utilized the product for weathercast and disaster risk reduction. These low latency products also bring important benefit to NWP around the world. JMA processes DR data acquired at the Kiyose station and the Showa station and distributes products derived from it to DBNet. This figure shows the history of LEO satellite received at Kiyose for the last 20 years. In the past, we received from the POS and Metop. Metop 16, 17, 18, 19, Metop-A. Now, we received in Kiyose NOAA 20 and 21, some NPP, and Metop-B and C. We would also like to receive such as Metop-SG A1, as Metop-SG A1, B1, and JPSS 4. Next, I will introduce the Kiyose station and the Showa station. The first is the Kiyose station, which is a receiving station owned and operated by JMA. This station is located in Kiyose, Tokyo. It has one antenna, and its specifications are as shown here. Currently, these 6 LEO satellites are being received. The reception range for NOAA 21 is as shown in light figure. And the range for the other satellite is approximately the same. And we plan to receive data from Metop-SG A1, Metop-SG B1, and JPSS 4. The next is I will talk about the Showa station. The Showa station is Antarctica is operated by the National Institute of Polar Research, NIPR. NIPR is a Japanese research institute that conducts research on Antarctic and Arctic. NIPR receives data from LEO satellites for its research activities and transfer the DR data to MSC. The Showa station has two antennas, one for the L band and S band, and the other for the X band. For receive data from these satellites, Metop-SG, some NBP, NOAA-20, and Aqua. This slide shows the processing and distribution of DR data in MSC. All data received at the Kiyose station is sent to the data processing system in MSC. On the other hand, only the microwave sounder data expected from data received at the Showa station is sent to MSC. Because of the limited capability of the communication lines from Showa to Japan. The DR data are then converted to level 1 data by the processing system. The level 1 data are sent to DBNet via GTS and to the GMS NWP center via GMS local network. RDR of ATMS and CURIS products at MSC are provided to SSEC at University of Wisconsin. And then level 1 data are made and distributed by SSEC. This slide shows how CSPP is used in DR data processing in MSC. We are currently using CSPP SDR version 4.1.1 to create SDR files. The created SDR files of ATMS and CURIS are converted to Level 1C format by AAPP. And these Level 1C files are used in GMS and WP. And we convert PR's data from SDR to GMS internal format to use it for monitoring volcanic ash and sea ice monitoring. Now, I would like to introduce how GMA users use DR data. Let's look at them in the following slide. The first one is about numerical weather prediction. A lot of DR data are used in GMS and WP models. These pie charts show the percentage of DR data from Kiyose and Showa among the LEO satellite data used in GMS global analysis and mesoscale analysis. And the pie chart, red color is GMA received DR data, and orange is DBNet data, and ash color is global data. In the global early analysis, with a long data cutoff time, 2 hours, 20 minutes, the percentage of data from Kiyose and Showa is about 1% to 5%. While in the mesoscale analysis, with a short data cutoff time, the percentage ranges from 9% to 25%. The DR data is variable for GMS operational NWP system, especially for short data cutoff time system. Next, volcanic ash monitoring. GMA operators, Tokyo VAAC, and providers volcanic ash advisories in the East Asia, Northwest Pacific Ocean, and part of the Arctic and Arctic Circle. Tokyo VAC use satellite data to monitor volcanic ash in the regions. DR data from LEO satellites are particularly useful for high latitude volcanic ash, where geo satellites have low resolution. This infrared image is of NOAA 90 AVHR data shows ash ejected from the Khrushchevskoye volcano on the Kamchatka Peninsula. The next slide is about sea ice monitoring. The Sea of Okhotsk is located in the north of Japan, and the southernmost sea in the northern hemisphere, where sea ice is observed across a wide area. Sea ice hinders marine output, damages fishing facilities, and obstructs shipping lanes, leading to accidents at sea. GMA use DR data to monitor sea ice around Japan. This light image is RGB composite imagery created from Metop-SG AVHR data, which makes it easier to distinguish between cloud and sea ice. So far, I have discussed the processing and utilization of LEO data. However, CSPP also has capability for geo, and it appears that it can process data from Himawari 8 and 9 as well. Therefore, I would like to introduce an overview of the future satellite system Himawari 10, which is currently being planned by JMA. Now, I will introduce an overview of Himawari 10. Himawari 10 is the JMA's future satellite system. Its operational start is planned for 2030 focal year. One of its key features is a hyperspectral infrared sounder. This instrument is called the Geostationary Himawari Sounder, or GHMS. Hyperspectral infrared sounder can measure the vertical distribution of atmospheric temperature and water vapor. By assimilating these data into NWP models, we aim to improve forecast accuracy. Himawari 10 will also carry an imager. This is the Geostationary Himawari Imager, or GHMI. Compared to AHI on Himawari 8 and 9, it has more spectral band and improved spatial resolution for some bands. Now, I will explain GHMI in more detail. It uses a sensor similar to the one selected for GeoXO program, GXI. Compared to the AHI on Himawari 8 and 9, several aspects have been updated. This includes the number of bands, spatial resolution, central wave ranges, and observation sequences. I will go through these changes. First, look at the right figure. Two new observation bands have been added. The 1.38 micron band is used to observe high clouds such as cirrus. It is strongly affected by water vapor absorption. So lower clouds are not easily visible. By combining it with other bands, high cloud can be enhanced. The 5.15 band, micron band is useful for observing lower level water vapor. In the visible range, central wave ranges have changed. For Himawari 8 and 9, one band has centered at 0.51 micron. This is slightly different from the standard green wave range, and this wave range has been used for aerosol observation. For Himawari 10, it is changed to 0.55 micron, which is closer to true green. This will affect the RGB composite image. The next left slide, shown left side, please. Next is the observation area. Observation time has been reduced, allowing more frequent observations. The number of target area has increased from 1 to 4. I have 3 new areas, with a 5th for navigation. A dedicated Japan area has also been added, and the cover is expected in the east-west direction. Next, I will move on to GHMS. GHMS is a Fourier transfer spectrometer by L3 Harris. Its spectral range is shown in this figure. It has a spectral coverage similar to the GeoXO hyperspectral sounder GXS. This figure is a red line is GHMS, blue line is GXS, and orange line is IRS, green line is CRIS. However, the two sensors, GXS and GHMS, sensors are not identical, unlike GHMI and GXI. The observation channels are divided into long wave and mid wave infrared. There are about 650 channels in the long wave and about 900 in the mid wave. Within these ranges, many molecular absorption lines are present. This allows observation of atmospheric temperature, water vapor, and many gases. The spatial resolution at nadir is 4.1 kilometer. For other specification, please refer to the table. This table shows the observation coverage and intervals of GHMS. GHMS observes regions with a zenith angle of up to 60 degrees. Each location will be observation again every 60 minutes. The area around Japan is observed more frequently, every 15 minutes. GHMS also has configurable target areas observed at the same 15 minutes interval used for typhoon observation, etc. Next, I will move on to the data format of Himawari 10 observations. First, I will explain the data format of GHMI imager. For Himawari 8 and 9, there are 3 level 1 formats. First, HSD is a format unique to JMA. And the second, HRIT and LRIT are legacy format used by MTSAT. NetCDF has mainly been used for scientific research. For Himawari 10, this format will be unified into NetCDF. Using this widely used format will make data handling easier. The NetCDF data for Himawari 10 will include all information currently conducted in HSD. It will also include additional information such as where quality flags details are still under consideration. One important to note, the NetCDF data for Himawari 8 and 9 are different from these for Himawari 10. The former contains significantly less information than HSD. The next, I will explain the GHMS data format and observation method. GHMS observations are conducted using a method called step and stair observation. The observations are performed in units called stair. Observation stairs to next step, observation stair. Each stair covers an area of approximately 1,000 by 500 square. A full disk observation consists of 154 stairs. It takes 60 minutes to complete. For the Japan area, observations are conducted at 12 stairs, 3 times per hour. For target area, 2 stairs are performed 4 times per hour. The data acquired in this way are compiled into NetCDF format. The smallest unit of data is 1 stair. Principal component data are distributed. Future details are still under consideration. This concludes my presentation on Himawari 10. Finally, I would like to talk about the total summary of my presentation. In the first half, I introduced direct readout of LEO satellite at MSC and the utilization of CSPP software. At GMA, we generate satellite product using CSPP and apply them to weather forecast and disaster risk reduction. In the future, we would like to receive data from new satellites such as JPSS and Metop-SG. We also look forward to future updates and developers of CSPP. In the second half, I provided an overview of Himawari 10, which is currently being developed by JMA. Himawari 10 will carry both the imager GHMI and the hyperspectral infrared sounder GHMS. And it's expected to be used for a wide range of applications. I hope this presentation has given you some interest in the capabilities of Himawari 10. We would also be very pleased if data processing capability for Himawari 10 could be added to CSPP Geo in the future. This slide is my last. Thank you for your attention.
Thank you very much, Nasu. Do we have any questions? Graham, your hand shot up right away.
So I know that I understand that you're on the LEO side rather than the GEO side, but I'm wondering if you know the answer to a GEO question. Actually, I have a couple of questions. Do you know what the plan is for distribution of data from Himawari 10 with regards to direct broadcast or rebroadcast?
Not for direct broadcast. Used for next to we expected to provide data via ground-based system like Himawari Cloud Himawari Cloud. The detail under consideration.
Okay, so it sounds like the plan is to distribute the data via Himawari Cloud, and currently there's no plan to have a Himawari cast for Himawari 10.
We plan to use a next generation Himawari Cloud.
Okay.
Okay,
thank you. So my other question was, you mentioned your use of CSPP-Geo software for CSPP-Geo software for Himawari 8 and Himawari 9. Could you expand on that a little bit?
We not use Geo CSPP-Geo.
Oh, okay.
Okay.
Thank you.
Thank you.
And yes, Nick.
Thank you very much for your presentation. Could you just remind me again the expected launch date of Himawari 10, please? When will the Himawari 10 be launched, become operational?
Himawari 10 planned to launch it at 2030 focal year.
Okay, thank you very much.
Thank you.
Any other questions? Is there anything online? Okay. Thank you very much for your talk.
Thank you.
Okay, we will move on to our next speaker, Yanan Liu, who will talk about an integrated direct broadcast satellite data platform for real-time management, visualization, and applications of CSPP-derived products.
Good morning, everyone. My name is Yanan Liu from East China Normal University in Shanghai. It's my great pleasure to attend the CSPP users group meeting in Darmstadt. Today, I will present my recent work entitled An Integrated Direct Broadcast Satellite Data Platform for Real-Time Management, Visualization, and Applications of CSPP-Derived Products. I would also thank Alan, Lim, and Cassie from UW Medicine for their long-term support and collaboration. My presentation consists of 3 parts. First, I will briefly introduce direct broadcast and CSPP real-time processing system. Second, I will present satellite product management and visualization platform. Finally, I will introduce low latency AI retrieval and future applications. Let me start with the first part, direct broadcast and CSPP real-time processing system. The system is an XL-band direct broadcast reception system jointly established by East China Normal University and UW Medicine in 2010. The system supports near real-time reception of multiple polar orbiting system or satellite systems, including the JPSS series from NOAA, the Metop satellites from EUMETSAT, and China's Coyne series satellites. It provides continuously multi-sensor observations over East Asia and the West Pacific. The system supports and automated satellite tracking and reception scheduling. During the simultaneous satellite overpasses, the system performs priority-based reception control to optimize antenna usage and data acquisition efficiency. The platform also provides real-time visualization of optotracks, overpass timing, and spatial coverage, enabling continuous monitoring of the reception status. After satellite reception, the raw direct broadcast signals are processed through the CSPP pipeline to generate multiple levels of satellite products. The workflow starts from ADR, which are converted into SDR, including calibrated radiance, reflectance, and brightness temperature observations. These SDRs are then further processed into EDR, including atmospheric land surface and oceanic retrieval products. Finally, these products support downstream applications such as numerical weather for prediction, air quality forecasting, climate study, disaster monitoring, and resources management. One important capability of the system is the generation of real-time true color imagery from various observations. These images provides intuitive visualization of typhoon structure, cloud organization, and environmental conditions. It supports rapid situational awareness and disaster response. The system also supports the cloud property retrieval products from CSPP Clevex, including cloud mask, cloud top height, cloud top temperature, cloud phase, and cloud type products. The system supports cloud classification and cloud microphysical analysis. It's important for several weather monitoring and radiative studies. In addition to two-dimensional satellite products, the platform also supports visualization of atmospheric profile retrievals from new caps. These products are generated from combined CRIS and ATMS observations and include temperature and moisture profiles throughout the tropopause. The platform supports both horizontal distribution analysis and vertical sounding visualization, enabling rapid assessment of atmospheric thermodynamic structure and stability conditions. The system also supports atmospheric trace gas retrieval products, including carbon monoxide, carbon dioxide, methane, ozone, and several other atmospheric constituents. It provides important information for air quality monitoring, atmospheric chemistry studies, and greenhouse gas applications. Beyond atmospheric applications, the platform also supports land and ocean environmental products. These include vegetation indices, land surface temperature, and sea surface temperature products derived from satellite observations. Such datasets are widely used in ecosystem monitoring, agriculture applications, urban studies, and marine environmental analysis. Finally, these satellite products are further integrated into downstream environmental applications, such as satellite products assimilating to regional numeric prediction systems, aerosol products combined with trajectory analysis for air quality forecasting, as well as support several weather and environment monitoring applications. Next, I will introduce part 2, satellite product management and visualization platform. With the rapid growth of satellite products, we have an increasing volume of SDR-EDR products from multiple sensor and multi-source observations with high frequency and real-time updates. This brings us new challenges, including massive data storage and management, efficient visualization, and rapid access in the active analysis of 2D and 3D products, as well as real-time operational applications. So therefore, a unified satellite intelligence platform is required for real-time management, visualization, and applications of CSPP-derived products. This slide shows the overall architecture of the satellite product intelligence service platform. This platform is organized into 3 major layers. At the bottom layers is data layer, including it integrates meteorological and environmental models, remote sensing, radar, and observation data. The middle layer is provides core service, including data service such as data acquisition, metadata, model service such as scenario collection, and map service such as spatial temporal scope and data thin and projection rendering. Analysis service such as spatial analysis, statistical analysis, product service such as map products in active production, early warning and forecast service such as future area extraction, as well as management service such as multi-source data and process monitoring. At the top layer provides application support layer, including specialized applications, web-based visualization, data sharing, and decision support. Several core technologies support the satellite intelligence platform. First is high-performance distributed architecture. It's built on an open-source database system with robust spatial processing capabilities. Second is massive atmospheric data visualization and mining. It enables direct raw data ingestion with real-time second-level rendering. Third is cross-platform big data sharing. It seamlessly connects multi-source atmospheric spatial temporal data with numeric models. Finally, the system supports online driven atmospheric numeric models. One key capability of the platform is in the active visualization of meteorological and environment datasets. It supports both scalar fields and vector fields, including contour maps, wind vectors, and environment overlays. Users can perform interactive zooming, temporal animation, playback, and multi-layer analysis directly within the web interface. This exam demonstrates the interactive visualization capability for CSPP cloud products. The platform supports seamless zooming and regional analysis for operational with monitoring application. Beyond 2D products, the platform also supports interactive analysis of atmospheric profile retrievals from new caps. Visualize some dynamic fields horizontally and select any individual pixel to display the corresponding vertical profile. This capability enables rapid analysis of atmospheric thermodynamic structure and stability conditions in real time. The system also supports flexible data management for multi-source environmental products. It supports automatic ingestion and indexing of multiple data formats, including NetCDF, HDF products, and so on. The system automatically extracts spatial temporal metadata and supports different grid structures, enabling efficient integration of newly generated CSPP products. Okay, the last part is low latency AI retrieval and future applications. Although modern satellite systems can provide large amounts of environment products in near real time, some advanced physical retrieval algorithms still remain computationally expensive and time-consuming. This limit becomes increasingly important for large-scale operational applications and rapid response environment monitoring. Therefore, AI retrieval frameworks provide a promising pathway for next-generation low-latency satellite applications. Here, I take AI-based methane vertical profile retrieval as an example. Most existing methane satellite retrievals from shortwave infrared sensors merely provide column concentrations with limited vertical profile information. In contrast, some infrared hyperspectral sounders, such as CRIS, YASI, provide valuable sensitivity to the vertical structure of methane throughout the troposphere. However, traditional optimal estimation retrievals are computationally expensive, while many existing machine learning approaches lack physical constraints and some dynamic decoupling mechanism. Therefore, our goal is to develop a physical constraint AI framework for rapid methane vertical profile retrieval from CRIS observations. The framework integrates CRIS hyperspectral observations, CAMS methane profiles, which is trace gases analysis data, and EI5 meteorological fields. We perform physically constrained channel selection based on Jacobi sensitive analysis, observational consistency, and redundancy reduction. A dual branch deep learning framework is developed to separately characterize methane spectral information and the meteorological background information. This slide shows multiple dimensional composite channel selection strategy. Based on Artov-Jacobi analysis, we identify methane-sensitive channels by M, means methane-sensitive metrics, and P metrics, which means a methane purity index, and provide a physically interpretable basis for channel selection based on observation minus background matched data sets as the root mean square error, RMSE, and R-square coefficient of determination identify stable and reliable channels under real observation conditions. At last, we developed a composite channel selection index to integrate physical sensitive and observational consistency. Here the M and the P index both show strong physical consistency in characterizing target gas response, but fail to identify channels heavily affected by instrument noise or model error. And the top 50 by RMSE are relatively scattered with lower information content. Top 50 by R-square are overly concentrated in localized regions, risking redundancy from structurally similar channels. Jointly incorporating physical sensitive and observational consistency achieves unified multi-dimension constraints, redundant high noise and low information channels while balancing effectiveness and stability. This slide shows dual branch deep learning architecture with thermodynamic decoupling. The primary branch uses 1D CNN to extract methane spectral features. The auxiliary branch uses a transformer encoder to characterize meteorological background information. And the cross-attention fuses features from both branches and decouples meteorological background interference and improve methane retrieval. The physical constraint channel selection improves the quality of methane-sensitive spectral inputs and reduces thermodynamic contamination. And the dual branch framework further improves retrieval performance significantly, reducing RMSE and bias throughout the troposphere. The largest improvement occurs in the 600 to 800 hectopascal, where temperature interference is strongest. To evaluate model robustness, we conducted an independent cross-year validation experiment as a completion with operational new CAPS products. The model was trained using 2021 data and evaluated using an independent 2022 dataset. Compared with the operational new CAPS product, the proposed framework shows substantially improved consistency with atmospheric analysis CAMS data, with low RMSE and more stable retrieval performance across the troposphere. This slide shows the spatial structure of retrieval methane profiles. The retrieval methane fields successfully reproduce the large-scale spatial distribution patterns over eastern China. Compared with new caps, the proposed framework best preserves fine-scale spatial variability, particularly in the lower troposphere and near the surface. These results demonstrate the potential of AI-enhanced therm-infrared retrievals for future high-resolution atmospheric composition applications. In summary, we developed an end-to-end framework for real-time direct broadcast satellite processing, visualization, and AI-enhanced retrieval applications. The system supports augmented CSPP processing, interactive environmental visualization, and physics constrained AI retrievals for atmospheric composition monitoring. Future work will focus on integrating AI-based retrieval algorithms directly into operational direct broadcast processing systems for next-generation low-latency satellite applications. Okay, that's all. Thanks for your attention.
Are there any questions? Yes, Satya.
Very nice presentation over here at the back. Couple of questions. How did you verify and validate your AI methane retrievals? The second question, how do you plan to use them? What application?
Okay. The validation with AI-based, because we just can get the trace gases profile from CAMS, because only CAMS analysis data provide the profile information. So we validation based on the CAMS analysis data. The second question about plan to use them application. Because the AI-based algorithm transfer it into application, I think still need a false application with ground-based observations and other platform data to cross-validation. In future, we hope this AI-based algorithm can integrate it into our direct broadcast and compared with new caps in parallel, I think. Thank you for your question.
Thank you.
Any other questions?
So how much benefit we are getting from AI rather than using the traditional retrieval? AI approaches you have been started using for product generation.
I think we are running in parallel, maybe 1 year, just a comparison. But future, we hopefully use AI replace the currently consuming time algorithm. Yeah.
So what is the time difference of product generation?
I think for new caps, maybe 5 to 10 minutes, but AI, I think less than 1 minute.
Okay. So it's a GPU. We have a separate architecture for this GPU cores.
Who use it?
GPU.
GPU. Yeah. I think only when you train the AI model, maybe we can use a GPU. But currently, based on the CPU, it also will be okay for experiment. Yeah.
Thank you.
Thank you.
Okay, Leon, you have a question?
Yeah, just a quick question. So, by method, are you aware of any users of dual broadcast interested using low latency messaging data? Just curious. Thank you.
I think maybe for operational this time as a short term will be okay. But for some disaster scenarios, maybe the time is more important. I think for the operational government, like environmental protection agency or meteorological agency.
Thank you, Yanan.
Thank you.
Okay, thank you very much.
Oh, thank you.
Okay. So we will move on to our final speaker before we have a group photo and then break for lunch. So I can introduce Antoine Jeanjean, who will be giving a presentation on a technical approach for EUMETSAT regional services, including EARS, Metop-SG, AWS, and Sterna. Oh, I'm sorry, I did not see. My apologies, Georgios as well. I did not see you that you were here, but co-presenters. So my sincere apologies for not seeing you.
Okay, so good morning. The presentation before lunch is always the best. So we'll end this morning session with the technical approach for EUMETSAT regional services. I will present the first part of this presentation focusing on the systems, and Georgios will do the second part focusing on the monitoring tool used by operation here in EUMETSAT. So as I said, I focus first on the system, its overview, the components, some system we're using as well for data consolidation, the timeliness of our services, the environment we use, and some software deployment processes. And Georgios will conclude with our monitoring tool used for operation. In EUMETSAT, we have this is an overview for our regional services. We have the regional core station, which are composed of an antenna, a baseband unit, and product processing node. I will detail each of these boxes later on in the presentation with slides. And then in our headquarters, we have as well some data processing system, dissemination system, and a retransmission server, which again, I will detail later on. This is providing an overview for now. The key message in this slide is you have EUMETSAT regional services are EARS, EPSSG, and EPS Sterna. They each support some satellite family, and in EARS it is the Fengyong 3, the Metop and the NOAA, and EPSSG and EPS Sterna are self-explanatory. The processing of EARS is done locally in the station, while for Sterna and EPSSG, the data processing system is located in the headquarters. And this presentation will mainly focus on the EARS, the technical approach used for the EARS services of Fengyong 3, Metop, and NOAA. The EUMETSAT regional core station are composed of two antennas, at least. Some of them, they have 3 reception chains. They are each connected to a baseband unit. In our case, we use at the moment Mios Polar V5, and they will be upgraded this year to Mios Polar V12. We have as well 2 processing server, which we call PPN, and then our communication system for routing data to headquarters. In 2020, the EUMETSAT regional orchestration have been harmonized. And this was done by a colleague in the room led by Carlos Cabanas. Before this activity, each station had hardware heterogeneity. And now in 2025, there was as well another project that I led, which was called ECNU, supported by people in the room as well. I can mention them. Georgios was part of it, Eduardo and Jorge in the back. And we upgraded the product processing server to a new hardware and software platform. And today I changed slightly my job, so I have handed over the responsibility of the processing system to Fernando Ibanez, is here in the room as well. This homogeneity of having 5 stations homogenized provide numerous benefits. Standardized hardware, so unified spare parts, similar type of anomaly across the ears network. Standard operation and monitoring. The software as well is unified, and the simplified deployment processes, and the contract as well to maintain 5 stations is harmonized. So a larger contract versus numerous smaller contract. So a lot of benefit to harmonize your system. Our station, I will pass quickly, but it's always nice to see that ears as a EUMETSAT regional core station are composed of very different locations. We have Athens, Maspalomas, Lannion, Svalbard, and Kangerlussuaq. I couldn't get a picture on the ground of Kangerlussuaq, so you have the Google Earth view there. And then we also have the EUMETSAT. We have and when you do the tour of EUMETSAT, maybe you will see it. It's on top of our data center. We have a test reception chain. And this is very useful to test new deployment of system. For example, when we have the new MEOS 12, they will be tested with this reception chain before they are installed in the operational station. So now we will dig in each of these, when we break down the system in smaller parts, we have in each of the regional core station a product processing node. So we call that the PPN. And this system is interfacing at the station with the MEOS to receive payload data. And from headquarters, we have the retransmission server that is providing auxiliary data. And the system also interfaces with our dissemination system to disseminate the product. The main function of the PPN is data processing to generate product for the Fengyong 3, Metop, and NOAA satellite families. Orchestration to orchestrate generation of product. So here we have all software application Dockerized. In EUMETSAT, we use Docker. It's also orchestrating, obviously, the auxiliary data and the dissemination. The end-to-end timeliness of these services are within 20 minutes. There will be a dedicated slide later on in the presentation. And a word as well that for us, we've had very positive experience. So this is a CSPP user conference. And we had very good feedback to give to a colleague here from Wisconsin that, for example, when we onboarded NOAA 21, it's usually a seamless, out of the box, we download, it works. The quality of the product is great. So thank you for that, for running, and providing software good quality that is also well maintained. When we have anomaly, it usually responds on quite fast. So thank you for the support on that. Regarding the retransmission server, so this is a system we have in the headquarters. It is not connected to the internet. It gets data via other systems, but for security reasons, all the EUMETSAT systems are offline. So we access them by separate. It's quite, you have several steps to get access to them. So via other system from internet, we have the TLE, the two-line elements, and the auxiliary data. You have, again, an orchestrator that is based on a EUMETSAT software. And what the RTS does, it provides two-line element and schedule to the MEOS in the core station. So you have a centralized scheduling. It also provides auxiliary to product processing nodes. And there is something new here, is we have a data consolidation. And this is a removal of duplicated data between the regional station for the imager services, which are for AVHR, MERCI, and VIRS. So you may think, why are we removing data duplication between for only some services? So there is a reason. Is first, we disseminate a regional passes that is passing over several stations, and it is also saving bandwidth cost for the UMETcast dissemination. I will come back to that in the next slide. So there you have an example of regional passes for Metop-SG, AVHR on 12th of May. So you see you have 26 minutes, 20 segments of 1 minute, and this is after dissemination. FY3D, you have an example there for MERCI and NOAA 20, and this one I took it because you can see that you had a pass there of Athens and then Svalbard and Kangerlussuaq, and you have a small gap between stations, so it was not a fully complete one, so this is on purpose. Okay, so the benefit of data consolidation is that all regional services in EUMETSAT are disseminated via EUMETCAST, which is a geo-relay satellite. And the bandwidth cost for data dissemination is high. So the removal of data duplicate provides significant cost benefits as the imager services and cloud product generated from imager data as the largest product in size. So now I'm going to switch to the table here. You have the EARS services, the instrument type, the daily data volume in gigabyte, and it is sorted by daily data volume. And you can see that when you look at imager and cloud type instruments, it makes 90% of the daily data volumes. And these are the services that are consolidated. So by removing data duplicate for these services, it saves basically EUMETSAT a lot of money. To further decrease bandwidth cost, you can see that the most consuming services in terms of bandwidth is VIRS. So there is a EUMETSAT software that is called Compact VIRS. So VIRS, despite being the first on top of that, these are compacted. So there is compression software that decreases even more the size of VIRS. And then the rest of the services, they make around 10% of the daily data volume. Now, I think for those that are in the community, you know that regional services live on timeliness. And when the EARS-NG system was designed and built, it was really designed in mind of having the best possible timeliness. And there here for last month, the average timeliness for the EARS services. And you can see that they are all below 20 minutes. And the imager, with the data consolidation, you have, that I could mention as well, that RTSTPS is run in server mode. So we have RDR granule being generated live during the pass. So yes, I mean, I think the number here, they speak for themselves. I took ATMS to have a look at a bit more in spread between the timeliness. So we have around 60% of data disseminated in less than 10 minutes. 80% is disseminated between 10 and 15 minutes. Then 3%, 15, 20 minutes. You had, there it says 0% over 20 minutes, but I had a look, you had one case where we had 35 minutes, but it didn't make up the small percentage number. But as I said again, I think these numbers speak for themselves, and this system is something we are quite proud to have built, and that is, yeah, numbers speak for them. A word on environments that are used. So in EUMETSAT, we have 3 environments for the regional services. We have an operational environment. This is an environment from which the regional services are run operationally. We have a validation environment where we validate new software patches and new elements before deploying into operation. And this is Georgios that is approving when we deploy services there. Georgios will approve and then it will go to operation. And we have as well the development system on top of our data center where we do the first round of implementation and tests. In terms of configuration control, all software and hardware deployed in VAL and OP environment are done under configuration control, which means that we're deploying on the RPM version and Docker Harbor version. And then as well, you have here this diagram that you see on the right is how we, in our technical baseline, we describe environments like the dev, the VAL, the OP, and in EUMETSAT we use a software called Enterprise Architect, which is basically all the system here are in this central, let's say, Enterprise Architect model together, where you can draw dependency and interfaces. So, for example, the MTG system, EPSSG, dissemination, etc. So they are all linked together in this central modeling tool for designing and being able to simulate future system and interaction. The last slide, I think I'm doing okay with time. So in terms of automated software deployment workflow, so we have streamlined software deployment with automation and package management from Git commit to production with CI/CD and YUM. So what do I mean? You have several steps where our software is in source control in GitLab. Every commit can trigger CI/CD pipeline with automated tests to detect early detection in terms of quality or defect in the code. If the tests are successful, it goes in the next step, which is build-like packaging. So this creates RPM, which is uploaded to a EUMETSAT Nexus server. And this provides versioning and traceability. And then once the RPM, we have Docker as well, it is also automated for Docker. Once the software is uploaded in Nexus in our development system, we can run YUM update, for example, or APP version or YUM update, whatever software is being updated, and it will automatically download the latest RPM version. And this provides fast validation in a production-like environment. And the last stage is the same step in our validation and operational system. So we use the same YUM update after all the validation tests have been conducted. And with this approach, we found that it's providing consistency, high reliability, and deployment confidence that George can probably witness to that. So when we deploy software in operation, we usually have no issue whatsoever. And it works out of the box because of these previous steps. Now I give it to Georgios that will present our operational tool.
Thank you for me. So as already mentioned, EARS consists of 11 instrument data services. The ASCAT, the ATOS, AVHRR, EASI, NWCIN, since CSNG, we have AVHRR and VIRS, ATMS, GRIS, VIRS, VAS, MERCI, and MWRI. The service performance, as already mentioned, is measured in terms of timeliness. The current requirement is 30 minutes, but as already mentioned by Antoine, we have managed with ESNG to decrease it to less than 20 minutes. The 5 core stations are monitored by the local operators, but also centrally here by the EUMETSAT controllers. All the services are monitoring each one independently And from all stations, we have given access to some of the EUMETSAT monitoring tools. Each station has at least 2 antennas, except LANOT that has 3 antenna chains, and Svalbard where we have the CDAs that are capturing the Metop satellites, and the rest 2 antennas, the SG 188 and SG7 that are capturing the rest of the satellites. The data line connections that we currently have is with Athens, dedicated PCW data line 100 Mbps. And we are working to have a backup line, the Giant, 1 Gbps. We hope that it will be operationally in Q3 this year. For Mas Palomas, the prime is the dedicated PCW, 100 Mbps, and we have a backup line, Giant, 1 Gbps. For Kangalusak, we have only 1 data line, PCW, 100 Mbps, and for LANOT, the same, and we expect to have a backup line that will be operational in Q1 next year. For Svalbard, we are using the Giant S prime, 200 Mbps, and we have a backup KSAT link in case of failure with 100 Mbps. It is important to have backup lines because we have seen that this is a single point of failure. So we had an incident, for example, in Athens 2 years ago, where we lost the PCW for 2 days. So there is a need to have a backup line for each station. The tools that we are currently using for monitoring the system is SMART. SMART is a scheduling, monitoring, and analysis and reporting tool that is available to the EUMETSAT and station operators. We have the GEMS, a generic event monitoring system that produces events for every push or problem that a system has, that is currently available to the EUMETSAT operators. We have the MEOS GUIs that are provided by the MEOS software, and this is available to EUMETSAT station operators. We also have the MEOS web reports, also available to both EUMETSAT and station operators. We have the OP5 that is based on Nigel's software that is available to EUMETSAT operators. We have a new tool that was introduced with ESNG, that is a station antenna rebalance tool. That means that in case of antenna chain failure, we can move all passes with a GUI using this tool. This tool was implemented by my colleagues, Eduardo and Jorge here at EUMETSAT, and helped a lot, especially if we have a failure during the non-working hours. And of course, at the end are the quality monitoring pages from NWP and NWC SAF that are both available to EUMETSAT and station operators. This is the first and the main tool that we use for monitoring. It's the SMART, and each service has a dedicated SMART viewer. So we have usually we have 3 screens that we split the ES products. The first is monitoring the ATOS, AVHRR, ASCAT, and IASI. The second, ATMS, CRIS, VIRS, and NWC VIRS.
and the rest are monitored by the third smart group. This tool, as I said, is available also to the station operators. They have a dedicated account and they can log in and open this tool. This is an example of the Athens station. They have a big screen that they can see in real time the flow end to end for all the year's products. This tool has also some reporting tools that, for example, they can they can take some monthly reports for scheduled, acquired, and missing passes. This is an example, for example, for Athens for July 2025, for Athens and LANOT. GEMS is a tool, as I said, that is available only for EUMETSAT operators, and you are getting events for all the processing that are running on all ER systems, MEOS systems, PPNs, and RTS. So in case of a problem, they are getting an alarm and they react accordingly. For example, you see the red one where some alarms coming from the Athens station. This is the MEOS GUI. This is the latest version that we currently have installed in all operational systems, the version 5.9.1. And this is available to both EUMETSAT and station operators. Usually, the stations have opened these two GUIs in real time at the operator room. This is the web reports. So you can see all the process from the start of the acquisition till the end of the local processing. And in case of an issue, you can check the signal, all the decoder, log status, and information like that. So you get all the needed information in case you want to investigate a case. This is the OP5 monitoring tool that, as I said, is based on Negios. And we have all the year's servers and IT components. And you can check in real time, not only the hardware problems, but also the processes that are running. So in case a processing is failing, then you get alarms and you can react immediately. This is the tool, the antennas rebalance tool. This is the most important tool that the controller is using in case of an antenna failure. You can see, for example, for Athens station, you have the two antenna chains. With green are the passes that are acquired from each antenna chain, and the controller can, with just some clicks, they can move passes from one antenna chain to the other and rebalance the antennas in real time. This is a very useful tool, as I said, in case of an antenna chain failure. And finally, these are the known NWP and NWC SAF quality monitoring pages. Usually we are checking this every morning to check if the quality of the products that we disseminate to the end users are okay. And that's it. Let me know.
Well, thank you very much, Antoine and Georgios. Are there any questions? Yes, go ahead.
Hello, thank you for the presentation. I have a question about the Mercy instrument for Fangyun 3E. Is it planned to include it also in the distribution at any point, or is it just too expensive in terms of bandwidth and what you can afford? And the reason I ask is because it has quite a unique orbit that observes Earth when no other satellite does.
Yes, I can reply. So you mean FY3G, no, the elliptical orbit?
I mean the Mercy LL.
Mercy LL,
Yeah.
yes. So we are civil servants, so user driven here. So the services that are disseminated are requested by user that are funding EUMETSAT, and they have not requested yet Mercy low light. So that's why it is not disseminated. If in the future this is of interest to the user and they want to have it done, we will implement it. But at the moment, it has not been requested.
Sorry, follow up. And when can I request this as a user?
Okay, then we can speak with Coyne after. Yeah.
Thank you.
Other questions? Liam, did you have one?
Yes, thank you, gentlemen, for your very interesting presentation. Antoine, in your presentation, you talked about the timeliness for the various sensor processing, ATMS, CRIS, YASI, and so on. The timeliness numbers, are they measured from the beginning of the pass or relative average to the center of the pass?
Yes,
how are they defined?
From sensing time to user reception.
Okay, sensing time to user reception. Okay.
So end-to-end. Yeah.
Okay.
So beginning of pass to when it goes through the whole system up to the user with the UMETCAST antenna in the location. Yeah.
Any other questions?
So the data archival level 0, you'll keep it or you are going to delete once the products are generated, whatever the received data.
Yeah, we have in the processing node an archive of 24 hours. So we keep a local archive, and then there is an automated housekeeping that is, like a rolling. So anything older than 24 hours gets deleted. Obviously, for the auxiliary file and other disks, we keep it a bit longer. But the raw data, level 0, intermediate product as well, they're heavy. So we keep them for 24 hours.
Yes, Bruce.
I think in your presentation you mentioned this isn't the word you use, but it's the one that I use in my head when I read it, was deduplicating your products and kind of combining them. At what level of the processing chain are you handling the duplicate products?
Yeah, that's an interesting question, because when we kicked off the project, we thought that doing it at raw data would be, a good shot. And then in the end, we are doing it at level 1. And the reason for doing it, so you have, the processing is done in the station. So each of the station basically goes up to RTS-TPS in server mode, live generation of RDR. And when you have the granule with context, you trigger the VS processing. And this is done in all the station. And then there is an SQL database here centralized that is basically receiving, when VS granule are generated, the completeness of the granule. Is it incomplete? Is it complete? Plus some of the quality parameter that you have within your level 1. And then you have a central decision making on top of the SQL database that is then, letting which station know, deciding which station to take the granule and then goes for dissemination. And it runs, we used to have a previous system before that was very difficult to maintain. And now with this approach of basically an SQL with, satellite, segment start, segment end, in 500 line of codes on top of the SQL, you have something very simple that is working well. So it's a very simple software that replaced a very complicated one.
Okay, thank you, gentlemen. And I think we can give all of our speakers in this session a round of applause. So just one note before we break for the group photo regarding Nigel's presentation this morning. I know several people, including you, Antoine, had a question. He did get back to me, and I will put them into Slido for anyone who wants to see the review. So just a second. This window. So for example, this is what it'll look. So I will just have replies under each one. So you should be able to go back to Slido, and I will let everyone know when the answers from Nigel are included. So I think that ends for our group for this session. We return to the group photo, and I'll hand it over to Liam.
So Axel is on her way to. Oh, there she is. Okay. So we'll do the group photo first, and then for lunch, it's at the cafeteria, which is just across the way, outside over here. Just follow the crowd. If you are not a UMETSAT employee, I have a lunch coupon for you. So please see me before you leave the room to get your lunch coupon for today. So
can I just in the canteen there's a choice of some starters and some main courses. There's two sides to the canteen. You'll get the same the same food on both sides. There's normally 4 different choices: a vegetarian, a fish, and two kind of meat choices. There's also a salad bar, and your lunch voucher will cover you to take any of the combination of those things that you want.
Okay, sure.